I'm Xiao. I'm an associate professor at Arizona State University. I'm here to present our lab's latest research on cyber threat detection systems. This is a collaboration work with my collaborators, and unfortunately they could not be here, so I will present on behalf of them, but the credits belong to the hardworking students. So advanced cyber attacks, such as advanced persistent threats, has penetrated into many well-protected organizations, causing significant financial losses. For example, the SolarWinds hacks caused more than 18,000 customers to download malware-tainted apps, and the Colonial Pipeline cyber attack caused at least 12,000 gas stations to run dry, resulting in a loss of over $10 billion. These advanced cyber attacks combines multiple advanced attack techniques, such as zero-day fireless attack and living off the land, making the entire attack more difficult to detect and analyze. To combat these kind of advanced cyber attacks, these days, provenance analysis has emerged as a promising solutions. So for provenance analysis, essentially, it leverages the system monitoring to collect the logs of system code from the kernels, and then use these system events to build a temporal graph. We call this temporal graph as a provenance graph. In a provenance graph, the nodes represent the system entities, such as files and process, and the edges represents the events. So as we can see from this example, we can easily use a provenance graph to show the contextual information of a suspicious attack events, and then to reveal the detailed attack steps. Seeing the potentials of provenance analysis, over the past 5 years, there are over 50 papers published in top security venues and top system venues for provenance analysis. However, in the industry, we don't see a widely adoption of this kind of technique. This is mainly due to two inherent limitations. First, provenance analysis has intolerable computational overhead when they trying to construct a provenance graph. For example, when we apply Unicorn, a state-of-the-art provenance analysis to monitor a cluster of 1,000 hosts, we actually need like about 350 megabytes per second bandwidth for the network transmission of the collected data. And then we need 3.6 terabytes per day to store the data, and we also need like more than 600 gigabytes of memory to perform the computations. These resource consumptions well exceeds the security budget for most security companies. And second, many of the provenance analysis approaches fail to achieve balances between precision and cost. Yeah, I think that many talk before me also talk about these issues before, right? So normally, the rule-based techniques, they are good at detecting the null attack, but they are severely limited by the expert knowledge and cannot detect unknown attacks. And the anomaly detection technique usually produce many false alarms and suffer from the notorious alarm fatigue problems. So to address these two fundamental limitations, we propose a normal systems, DISTDET, which synergistically combine distributed computing, anomaly detection, and false alarm filtering technique to analyzing and detecting advanced cyber attacks. In particular, our system is built based on 3 key insights. First, instead of using a centralized architecture as the existing provenance systems, we actually adopt a distributed architectures. So basically, we shift part of the detection workloads to the client side, and then we ask the clients only to send a summary graph instead of the whole set of the provenance log to the server. This will greatly reduce the network transmission cost. Second, we observe that false alarm typically possess some very unique properties. So the first property is that these false alarm normally represent the same benign behaviors that is reported over a short period of time. The second property is that we found out that many false alarms are actually related to the benign behaviors triggered by semantically similar commands. So you run some commands in a terminal and you start a process. But those benign processes, they tend to have very similar command parameters. And the third parameter is that the context for these alarms are generally known to represent some benign process. So we may find out some of the context of the alarms that actually you see many times before for some benign background process. So if we leverage these kind of unique properties, we will be able to develop an effective strategies to filter out false alarms. And finally, if we build a local model in a single host, the local model may have a lot of false alarm because the local model may only observe the partial behavior of some benign process. So if we can build a global model that can merge all the behavior from different hosts for the benign process, then we have a better view, and then we can use that to filter out false alarm. So next, I'm going to briefly introduce the detailed design of my approach. So our system has two sides. One is on the client side, and the other is on the server side. So on the client side, we do a chaining to build a local model. Basically, we provide a compact index that categorizing auditing events based on their property using a multi-layer tree. We call this tree as a hierarchical system event tree. This is a simple example to represent our host model built for a single host. So after the chaining period, any events that cannot be found in this model will be considered as an alarm. Once an alarm is detected, we are not going to send all the log of the events to the server. We are going to generate a summary graph we call an ASG. Essentially, an ASG consists of the process that initiates the suspicious behaviors and its ancestor and descendants within X and Y generations. So it's a very small graph that contains some very important information about the related process for this alarm. And after the ASGs are generated, we perform false alarm filtering on both client side and server side. So on the client side, we maintain a time window for each newly reported alarm. And all the subsequent alarms whose events are the same as the one that we have observed will be discarded. On the server side, we first try to find out the similar ASGs. So what we mean by similar ASG is like for every ASG, we have a alarm process, and then you have an associated command that you executed to run that process. So we are going to compare the semantic similarities between this kind of the command between these these ASGs. And for the ASG with very similar commands, we are going to merge it and only record the frequencies on top of the ASG. And the second step we do on the server side to filter the false alarm is to compute the anomaly score. So we design the anomaly score to focus on the rareness of the events. So each ASG contains some kinds, at least one alarmed process, and then have other set of like benign events because of the ancestor and the descendants. So we compute the anomaly score based on the frequency on the normal events that we found in the ASG and also the alarm event we found in the ASGs. And then we filter out the ASG whose anomaly score is below a threshold. And this threshold will be determined during the training period. We mentioned that we are going to build a local host model for each host. So, but this local model is very likely to only see some partial behavior of benign processes. So to mitigate this issue, we are going to build a global models in the server side. So in the server side, what we do is that we first identify the host that perform the similar services. For example, you may have a group of hosts that are providing the MongoDB services. We're expecting those hosts will have a similar services processes, right? So then we base on these kind of similar service processes, we cluster the host, and then we merge the behavior of the benign process in this cluster. In that way, we can derive a global model, and then we send this derived global model back to the clients, and the client can update their local model with this global view. This can also help reduce the false alarms. And we evaluate our systems, mostly focusing on the cost, on using our system, and the effectiveness of whether we can still maintain high detection precisions. So we have used three kinds of data sets. The first data set is the industry arena data set, where we deploy our systems in the real industry environments and then collect the data for a period of time. And the second data set we use is the DARPA TC data set, which is generated by the DARPA TC programs. And the third data set we use, we call the public arena data set. Is essentially we perform an insider attack and a lateral attack on our lab settings. And then we collect both the user log and the system audit log. This is because to compare with some related work like log to vec, we need the user logs as well. So here's the summary of our evaluations. First, the cost, right? So we show that our systems can successfully reduce the protection cost for each host from $3.4 US to $0.061 US. This is about like 56 times reductions. Second, we evaluate the effectiveness of our detections, right? We show that even by splitting, like adopting the distributed computing architecture, we can still maintain the detection F1 to at a high level, right? So essentially, we can achieve like 0.98 F1 for the industry arena and the DARPA TC dataset, and then we can achieve a F1 of 0.89 for the public arena dataset. We also compare with related work, and then we show that we outperform all the related work. And because we emphasize a lot in terms of the false alarming, so we also filtering, so we also measure that, right? So our results show that we will be able to reduce the false alarm from 230 per host per day to 0.71 false alarms per host per day, right? This is saving more than 99% of the manual effort in filtering out false alarms. This could be a big savings for security companies. And finally, we also deploy our systems in some collaborative companies for roughly 6 months, and we were able to successfully detect more than 900 attacks. And we show that we actually are more effective than any other existing endpoint detection and response tools. So before I conclude my talk, I would like to make a small advertisement for our upcoming paper, CCS paper, which performs a deeper analysis on how the industry view of like provenance analysis and why couldn't they adopt provenance analysis easily. Yeah, so please also come to our talk in CCS as well. Thank you. I'm ready to take questions. Yeah.
Thank you.